Good morning, everyone, and thank you for joining this advanced technical session at Postgres conference in San Jose. My name is Ibrar Ahmed, and today we are going to build a practical mental model for multi-master workflows using Postgres logical replication. We will start with the foundation, how physical replication streams the write-ahead log, why that model is excellent for high availability, and where it stops helping when applications need writes in more than one place. From there we will move into logical replication, publications, subscriptions, replication slots, identity strategy, conflict management, operational guardrails, automatic DDL replication, Zoden, and PGHSPOC. The point of this talk is not theory for its own sake. The point is to connect the diagrams, the SQL, and the production failure modes so that when you design an active-active system, you know exactly which problems you are accepting and which controls must be in place before go-live. Let me set expectations for the level of detail. This is an advanced session, so we will not stay at the marketing diagram level. We will look at the ordinary mechanics first, where a change is written, how Postgres remembers it, how another node consumes it, and what metadata is needed when more than one node can write. That foundation matters because multi-master systems usually fail in the gaps between concepts. A team may understand that replication exists, but miss that sequence values collide. They may understand that conflicts exist, but not decide which side wins before the incident. They may understand that a cluster spans regions, but not account for clock skew or a partition network. So as we go slide by slide, listen for the operational question behind each architecture choice. What would I monitor? What would I automate? And what rule would my team follow under pressure? That is the lens that turns this from a diagram into an operating model. One more framing point before we begin: multi-master is not a replacement for fundamentals. You still need backups, restore drills, schema review, and clear ownership of operational decisions. Active-active write capability raises the ceiling, but it also raises the cost of vague thinking. Throughout the session, treat every slide as an architecture review question you can ask in your own environment. Before we talk about multi-master, we need to anchor ourselves in physical replication, because many assumptions people carry into distributed Postgres systems begin here. Physical replication works at the storage level. When the primary commits a transaction, Postgres writes entries to the write-ahead log that describe the physical page changes. Those entries are streamed to standby servers, and the standbys replay them so they become byte-for-byte copies of the primary. That is why the slide emphasizes a full cluster copy, same data files, same page layout, same database state. This model is battle-tested for high availability. It gives you fast failover, strong durability, and a straightforward operational story. But it also has strict boundaries. You cannot replicate only selected tables, you cannot cross major versions safely using raw storage bytes, and the standby is not a writer. Physical replication gives you one source of truth with read-only copies. That is a great foundation, but it is not multi-master. One detail worth emphasizing is that physical replication is intentionally blind to business meaning. It does not know that a customer row changed, that an invoice was inserted, or that a tenant moved regions. It sees storage level change and reproduces storage level state. That blindness is a strength for failover because the standby is faithful. It is also the reason the model is rigid. You get the entire cluster, not a curated subset. You also inherit tight coupling to storage format and Postgres version. In real operations, this means physical replication is usually the first layer of resilience: one primary, one or more standbys, backups, archive retention, and tested failover. But when you need selective movement of data, live upgrade paths, or writable nodes in multiple places, you step outside what physical streaming was built to solve. The lesson is not to discard physical replication. The lesson is to respect its boundary and layer logical mechanisms where row-level meaning is required. In practice, this is why many teams keep physical replicas even when they adopt logical or multi-master patterns. Physical replicas are excellent for local failover, read scaling, and protecting against node loss. They are simply not a substitute for row-aware distribution. A mature architecture often uses both, physical replication for local resilience, logical mechanisms for controlled data movement and active-active behavior. Additional speaker note: physical replication is also a failure domain decision. A streaming standby is valuable only when it survives the same event that damaged the primary. Treat storage separation, promotion rehearsal, archived write-ahead log, monitoring, and application routing as part of the design, not as later operational details. Logical replication changes the unit of replication. Instead of shipping raw page bytes, Postgres decodes changes from the write-ahead log and sends logical row operations, inserts, updates, deletes, and truncates. The deck shows the two key objects, publications on the source side and subscriptions on the receiving side. A publication says which tables and which operations are available to replicate. A subscription connects to that publication and applies the changes on the target. This model is more flexible than physical replication. You can replicate a subset of tables. You can move data across major Postgres versions. You can filter columns or rows depending on the setup. Most importantly, logical replication speaks in database changes rather than storage blocks, so it becomes the primitive we can extend into more advanced topologies. But the native model still starts as publisher to subscriber. That directionality matters, and it shapes everything that follows. When you explain logical replication to an operations team, I find it useful to separate three responsibilities. First is decoding. Postgres reads the write-ahead log and translates low-level change records into logical row operations. Second is publication. The source decides which changes are visible to subscribers. Third is apply. The subscriber replays those logical operations into its local tables. Each part can fail differently. Decoding depends on retained write-ahead log and slots. Publication depends on table identity, privileges, and filters. Apply depends on compatible schema, constraints, and available workers. That is why logical replication troubleshooting should be systematic. Check whether the source retained the needed records, whether the publication exposes the expected table, whether the subscription is connected, and whether reply is blocked by schema or constraint errors. Once you see it as a pipeline, multi-master becomes a matter of making that pipeline bidirectional safely, not magically. A useful mental model is that logical replication exposes intent after the fact. The application executed SQL, Postgres stored the durable record, and decoding reconstructs the meaningful row change. That reconstruction is powerful, but it depends on the target being ready to apply it. If schema, identity, or constraints are mismatched, the logical stream becomes a queue of problems rather than a queue of changes. Technical correction for this slide: row filters, column lists, and cross-version logical replication depend on the Postgres release and on the supported upgrade direction. Present logical replication as a powerful compatibility tool, but not as a universal guarantee across every version pair or every publication feature. Let us walk through the SQL workflow on this slide in order. First, we create a replication slot on the publisher. The slot is the publisher's memory of how far the subscriber has consumed the change stream, and it is what prevents needed write-ahead log entries from being removed too early. Second, we create a publication. That defines the table set and operations that are eligible to flow out. Third, on the subscriber, we create the subscription that connects back to the publisher and starts applying changes. Fourth, we check status so we know whether the subscriber is connected, whether lag is under control, and whether reply is healthy. The important conference takeaway is that logical replication is not magic. It is a chain of explicit objects: slot, publication, subscription, and monitoring. If you understand that chain, troubleshooting becomes much more predictable. As we click through the terminal, notice that each SQL step creates an operational object you can later inspect. The replication slot has a name and a confirmed position. The publication has tables and operation types. The subscription has connection state, worker state, and lag. In a production runbook, those objects should appear in both setup and validation sections. It is not enough to run create subscription and assume replication exists. You should verify the slot is advancing, Confirm the subscriber is applying, watch for retained bytes, and test a controlled insert before handing the topology to applications. Also pay attention to naming. Slot names, publication names, and subscription names become your incident vocabulary. If you name them casually, debugging at 3 in the morning gets harder. A clean logical replication workflow is not just syntactically correct SQL, it is a set of named, observable contracts between nodes. For teams building runbooks, I recommend writing the expected query output next to every command. Do not only say, create slot, also say what slot name should appear, what state should advance, and which catalog view proves it. That turns setup into verification. It also lets a second engineer review the topology without relying on memory or tribal knowledge. Additional speaker note, publication and subscription look simple in a diagram, but production success depends on slot retention, apply speed, schema compatibility, and lag monitoring. Logical replication should have an owner for every dependency, because an unmanaged slot can become storage pressure and an unmanaged subscriber can become silent drift. This comparison slide is useful because it separates three patterns that often get mixed together. Physical streaming replication is a byte-for-byte copy. It is simple, reliable, and ideal for high availability, but the standby is read-only and follows the primary. Logical replication is row-level replication. It gives you table-level control, cross-version movement, and more flexible data distribution, but it is still fundamentally a one-way publisher-to-subscriber pipeline in core Postgres. Multi-master replication is a different operating model. Every node can accept writes, publish its own changes, and subscribe to changes from peers. That capability creates the business value, lower write latency, regional availability, and no single writer bottleneck. It also creates new responsibilities, conflict detection, identity management, loop prevention, schema discipline, monitoring, and split-brain protection. The rest of the talk is about handling those responsibilities deliberately. The comparison also helps choose the right tool instead of forcing every requirement into one replication model. If your requirement is warm standby failover in the same Postgres major version, physical streaming is usually simpler and more predictable. If your requirement is selective table movement, reporting replicas with filtered data, or a near zero downtime major upgrade, logical replication is the more appropriate primitive. If your requirement is local writes in multiple regions, neither of those alone is enough, you need active-active controls. A common mistake is to jump to multi-master because it sounds more available, without asking whether the workload actually needs multi-writer behavior. Multi-master increases design responsibility. If one region can own writes for a tenant, routing to an owner may give you most of the latency benefit with far fewer conflicts. The mature architecture is the one that matches replication model to business requirement, not the one with the most arrows on the diagram. This table is also a communication tool for stakeholders. When a business owner asks why we cannot simply turn on multi-master, this is the explanation. Different replication models optimize different guarantees. High availability, selective movement, and multi-writer locality are separate goals. Mixing them without naming trade-offs leads to overpromising. Naming them lets architecture, operations, and product agree on what the system is actually designed to do. Technical correction for this slide: core Postgres does not include native active-active multi-master by itself. The multi-master pattern is built with extensions, coordination, routing, identity rules, and conflict policy layered around logical replication concepts. That distinction matters for an engineering audience. This slide shows the core limitation very clearly. Native logical replication delivers changes one way, from a publisher to one or more subscribers. The subscriber receives and applies data changes, but there is no native reverse channel that turns the subscriber into an equal peer. If you simply create subscriptions in both directions without additional controls, you create a dangerous loop. A change can leave node A, arrive on node B, and then be republished back to node A as if it were new. Core logical replication was designed with a single source of truth in mind. That is why multi-master is not just a checkbox on top of standard logical replication. You need origin tracking, loop detection, conflict rules, identity strategy, and operational policy. The one-way model is not a weakness, it is a clean primitive. Multi-master is what you build when your requirements exceed that primitive. This one-way limitation is also why naive bidirectional setups are dangerous. Two subscriptions pointed at each other can look elegant in a lab until the first replicated change is treated as new input on the peer. Without origin tracking, the system cannot tell the difference between a local write and a remote write being echoed back. That distinction is the heart of loop prevention. You need metadata attached to each change that says, in effect, this change began on node A, so node A must not apply it again as a fresh local event. You also need a policy for what happens when a remote change touches a row that was changed locally before the remote write arrived. Core logical replication gives you the delivery mechanism. Multi-master requires the semantics around delivery, origin, ownership, conflict behavior, and convergence rules. The reverse channel is where many demonstrations become misleading. Seeing a row replicate in two directions is not the same as having a production-ready multi-master system. Production requires knowing whether that row originated here, whether applying it would violate ownership, whether a concurrent local update exists, and how the conflict rule is audited. Direction is easy. Safe direction is the work. Technical correction for this slide: the publisher owns the write-ahead log sender path, while the subscriber applies changes through logical replication workers. When explaining one-way delivery, keep sender-side and apply-side responsibilities separate so operators know where to inspect lag and backlog. Now we can look at the multi-master strategy. The diagram shows a peer-to-peer mesh. Each node is both a publisher and a subscriber. Node A publishes local changes to B and C. Node B publishes local changes to A and C. Node C does the same. From the application's perspective, writes can be accepted locally in more than one region. From the replication layer's perspective, every write needs metadata, where it originated, which peers have seen it, and whether applying it would conflict with local state. This is why the design pattern is not just bidirectional replication. It is disciplined active-active replication. Local writes replicate outward. Remote writes are applied with origin awareness. The cluster converges because every node follows the same deterministic rules. If you remember one thing from this slide, remember this: multi-master is a topology plus a rule system. The peer-to-peer mesh is attractive because it removes the single geographic choke point, but it also multiplies relationships. With 3 nodes, each node needs to understand 2 peers. With more nodes, the number of replication paths and monitoring points grows quickly. That does not mean the design is wrong, it means automation becomes non-negotiable. Publications, subscriptions, slots, credentials, conflict settings, and schema state must be generated consistently, not hand-built node by node. The application layer also has a role. If a user belongs to the US region, route routine writes to the US node. If a tenant is assigned to Europe, keep its primary write path there. Let the mesh provide resilience and convergence, but do not create unnecessary conflicts just because every node can technically accept writes. A healthy active-active design uses local writes intentionally, not randomly. Another design choice is full mesh versus more constrained topology. Full mesh maximizes peer equality, but it also increases connection count and operational surface area. Some deployments use regional grouping, ownership routing, or hub-assisted bootstrap to reduce complexity. The best topology is not the most symmetrical one, it is the one whose failure behavior the team can explain and rehearse. Additional speaker note: multi-master should solve a clear business need: local writes, regional resilience, write anywhere workflows, or lower latency for distributed teams. It is not a shortcut around data modeling. The design still needs identity rules, table ownership, conflict policy, operational tests, and a clear definition of which data is safe to write from multiple places. Before the deck moves into the harder problems, it gives us a readiness framework: SEMO. S is schema. Every replicated table must have a compatible schema on every node, and primary keys must be present and meaningful. I is identity. You cannot let independent nodes generate colliding keys and hope conflicts stay rare. And is monitoring. Replication lag, slot health, apply errors, and conflict rates must be visible before users notice impact. O is ownership. Even in a multi-master system, many workloads benefit from clear row or tenant ownership, so writes usually land on the node best positioned to own them. This checklist is intentionally practical. A multi-master design fails less often because of a clever algorithm and more often because one of these foundations was treated as optional. Schema, identity, monitoring, ownership, those are the go-live gates. SEMO is short, but it is a serious readiness test. Schema asks whether every node can apply the same changes without breaking constraints or apply workers. Identity asks whether new rows can be created independently without duplicate keys. Monitoring asks whether the team will see lag, slot retention, apply failures, and conflict rate before customers see inconsistent behavior. Operations asks whether recovery, failover, DDL changes, and node replacement have a rehearsed procedure. I like this checklist because it converts an architecture review into yes or no gates. If the answer to any pillar is vague, the system is not ready for production traffic. For example, if the identity answer is we use serial today and will fix it later, that is not a risk node, it is a blocker. If monitoring is we have logs, that is not enough. You need metrics, thresholds, and ownership. If you only have time for one readiness meeting before go-live, use SEMO as the agenda. Put schema, identity, monitoring, and operations on 4 rows. For each row, require evidence, DDL comparison, key strategy, dashboard links, runbook links, and named owners. If evidence is missing, postpone the launch. That is cheaper than discovering the gap during conflict resolution or failover. Here is the business reason this architecture matters, the single writer bottleneck. On the left side of the slide, many applications depend on one primary writer. Reads can scale, but writes still funnel through the same node. That creates latency for distant users, operational pressure during failover, and a hard ceiling during write-heavy workloads. On the right side, the multi-master model lets nodes accept writes locally while replicating changes outward to peers. That can reduce regional latency and remove the single writer as the only path to progress. But it does not remove physics. Network latency still exists. Conflicts are still possible. Schema drift is still dangerous. The value of multi-master is not that it makes distributed systems easy. The value is that it lets you choose availability and locality, provided you also implement the controls that make convergence safe. The single writer bottleneck is not only about throughput. It is also about geography and failure domains. If every write must cross an ocean to reach one primary, user experience and availability are tied to that path. During regional degradation, the application may still be alive locally but unable to commit because the writer is elsewhere. Multi-master changes that contract by allowing local progress. But the right side of the slide also implies a new kind of correctness work. If app A writes to node A and app B writes to node B, the database must reconcile the resulting histories. That means identities must be globally safe, conflicts must be deterministic, and network partitions must be fenced. The bottleneck disappears only if the surrounding rules are strong enough to prevent data divergence. In other words, active-active is not simply 3 primaries, it is 3 primaries plus a discipline for agreement. The after diagram is attractive, but every green checkmark should have a policy behind it. Node A can write what? For which tenants? During which health states? What happens when node B is reachable from users but not from peers? The answer should be encoded in routers, health checks, and fencing, not left to human judgment in the moment. Identity is one of the first practical problems teams hit. A standard serial or big serial sequence works beautifully on one primary because there is one place assigning numbers. In a multi-master cluster, independent nodes can generate the same value at the same time, and those values collide when replication applies the inserts. This interactive slide walks through the main strategies. UUIDs avoid central coordination and are often the safest default. Range allocation gives each node a non-overlapping numeric block. Composite keys combine a node identifier with a local sequence. Step sequences let each node advance by a different offset. The warning at the end is the important part: plain serial values are not a multi-master identity strategy. If keys can collide, replication will eventually surface that design mistake as an insert conflict. Fix identity before production traffic finds the problem for you. Sequence handling deserves more attention than it usually gets because key generation is often decided years before multi-master is considered. A serial column is local state. Two nodes both starting at 1 can generate identical values, and the conflict may not appear until replication tries to apply the second insert. UUIDs solve this by making identifiers globally unique without coordination, which is why they are often the safest choice for distributed write systems. Range allocation preserves numeric keys but requires operational discipline to assign and monitor ranges. Composite keys can be excellent when the application naturally understands node or tenant identity. Step sequences can work, but they encode topology assumptions into key generation. The broader point is this: identity is part of replication design. You cannot treat primary keys as an implementation detail once multiple nodes can create rows independently. When choosing an identity strategy, include downstream systems in the conversation. Analytics warehouses, caches, event streams, and audit logs may already assume integer keys. Changing to UUIDs can be right, but it must be deliberate. If you keep numeric keys, document allocation and exhaustion behavior. The worst identity strategy is the one nobody remembers when a new node is added. Once identity is under control, there are 4 structural challenges every multi-master system must solve. First, loops. A change must not bounce endlessly around the mesh, so every replicated write needs origin awareness. Second, conflicts. 2 nodes can update the same logical row before they see each other's changes. Third, ordering. Distributed writes do not arrive everywhere in the same sequence, so the system needs a deterministic rule for final state. Fourth, schema. The table definitions must remain compatible across all nodes or replication becomes unsafe. These are not edge cases. They are the normal cost of accepting writes in multiple places. The good news is that each problem has a known control. Tag origins, designed to reduce conflicts, use deterministic resolution rules, and manage schema as a cluster-wide operational process. These 4 problems are the framework for the rest of the talk. Loops are a replication metadata problem. Can the system recognize a change it has already seen? Identity is a data modeling problem. Can 2 nodes create rows without colliding? Conflicts are a workload and business semantics problem. What should happen when 2 places modify the same thing? Schema is an operational problem. Can every node understand the same row shape at the time a change arrives? Notice that each problem lives at a different layer. That is why database-only answers are incomplete. You need extension behavior for loop prevention, schema and migration discipline for DDL, application routing for ownership, and monitoring for early warning. Multi-master is a cross-layer design, and teams that treat it that way have fewer surprises. These 4 categories also help during incident triage. If replication is noisy, ask which category is failing. Are changes looping? Are keys colliding? Are rows conflicting? Is schema different? That classification narrows the investigation quickly. Without it, teams jump between logs, network checks, and application blame without a clear hypothesis. Conflict management starts with a simple hierarchy: avoid, route, resolve. Avoidance is best because the cheapest conflict is the one you never create. You can partition ownership by tenant, region, account, or key range, so most writes naturally go to the node that owns that data. Routing is the next layer. If the application knows row ownership, it can direct writes to the right node even when users connect elsewhere. Resolution is the final safety net, not the primary design. When 2 nodes really do modify the same logical data concurrently, the cluster needs a deterministic rule that every node applies the same way. This slide is a reminder that multi-master reliability is partly a database problem and partly an application architecture problem. Your conflict rate is usually designed long before the database sees the write. Avoidance is where you get the biggest return. If tenants have natural home regions, route writes there. If a table is append-only, design it so inserts never fight over the same key. If a workflow has a single owner for a business object, enforce that ownership in the right path. Routing is the practical mechanism that turns ownership into behavior. A write router can look up tenant, region, or object owner and send the request to the right node. It can also reject off-owner writes when accepting them would create ambiguity. Resolution is still necessary because outages, retries, admin scripts, and edge cases happen. But resolution should be the airbag, not the steering wheel. The more conflicts you avoid up front, the less often your deterministic rule needs to decide who loses data. A good conflict strategy should be visible to application developers. They need to know which fields can be merged, which objects have owners, which writes may be rejected, and which retries are safe. If developers treat every database error as retriable, they can amplify conflicts. If they understand ownership and idempotency, the database sees cleaner traffic. Additional speaker note: conflict management is about preserving business intent. A database can detect that two changes disagree, but it cannot always know whether the correct answer is last writer, merged columns, summed counters, or manual review. That policy must be designed and tested before production traffic depends on it. Let me separate conflict resolution into two slides so the model is easier to follow. First, update and delete conflicts. In an update conflict, two nodes modify the same logical row before either has seen the other change. If they changed different independent columns, a column-level merge may preserve both intents. If they changed the same column, you need a deterministic winner such as last committer wins, and that rule depends on reliable commit timestamp discipline. Delete update is different. One node removes the row while another updates it. There is no universal database answer. The application must define whether deletion is final, whether the update reinserts, or whether the row becomes logically inactive. The important rule is consistency. Every node must make the same decision from the same evidence. Technical correction for this slide: merging different columns is safe only when a deterministic merge rule has been designed and tested. The database can identify a conflict, but the business rule decides whether the result should be last writer, column merge, counter merge, or manual review. The second half is insert and custom merge behavior. Insert conflicts usually mean two nodes generated the same primary key. That is not a conflict you want to resolve after the fact. It is an identity strategy problem. Use UUIDs, non-overlapping ranges, composite keys, or another design that prevents duplicate keys before replication receives them. Custom merge conflicts are different. Suppose node A increments a counter by 3 and node B increments it by 5. Last committer wins would throw away one increment, which is wrong. The correct final value may be 8, and that requires a merge function or CRDT style rule that preserves both operations. This is why conflict resolution must be driven by business semantics, not by whichever write arrives last. This interactive terminal shows last committer wins using commit timestamps. The first step is enabling commit timestamp tracking in PostgreSQL and restarting the cluster. Once that is enabled, Postgres records a wall clock commit time for each transaction. Then we write on node A, write on node B, and resolve the conflict by choosing the later commit timestamp. The rule is simple and easy to explain, which is why teams like it. But the final click on the slide is the risk: clock skew. If node A's clock is ahead, node A can win conflicts even when its write was not truly later in real time. That is why NTP discipline is not a nice-to-have in this architecture. If your resolution rule depends on time, your clocks are part of your correctness model. Commit timestamps make last committer wins understandable, but they also make time part of the data model. Enabling track commit timestamp lets Postgres record commit time so a resolver can compare versions. In the example, node B commits later than node A, so node B wins. That is easy to explain to operators and application teams. But the clock skew step is the reason this slide exists. If clocks differ across nodes, later may only mean later on a bad clock. NTP, cronny, monitoring drift, and alerting on clock health become correctness controls, not generic infrastructure hygiene. Also remember that last committer wins is not appropriate for every domain. It may be fine for a cache-like preference value, but unacceptable for balances or inventory without compensating logic. Simple rules are valuable, but only when the business semantics match. Clock monitoring should be part of the same dashboard as replication health. If drift exceeds your threshold, conflict resolution based on time is suspect, even if replication lag is low. That means alerting on time synchronization is not noise. It protects the meaning of your rule. If the rule says later wins, later must mean the same thing on every node. Additional speaker note: commit timestamps are useful when the business truly accepts a winner-takes-all rule. They are dangerous when both rights carry independent meaning. The professional question is not whether last committer wins is available, it is whether the rule matches the data and whether losing one update is acceptable. There are three production forces you cannot wish away. The first is network latency. The round-trip time between nodes becomes the conflict window. The longer it takes for a write to reach peers, the more time another node has to make a conflicting write. The second is replication lag. A subscriber that is behind a serving state that may already be obsolete elsewhere, and a growing backlog can turn a small issue into a recovery event. The third is operational drift. If configuration, schema, extensions, or application routing differ between nodes, behavior will diverge even if replication is healthy. This slide is intentionally operational because multi-master success is not just about creating subscriptions. It is about keeping latency, lag, and drift inside known limits every day. Latency, lag, and drift show up in every real deployment. Latency defines the time window in which independent writes can collide. If nodes are close, the window is smaller. If nodes span continents, the window expands. Replication lag tells you how long a remote node is operating without the newest changes. Lag can be caused by write bursts, slow apply workers, disk pressure, network loss, or a blocked transaction. Drift is more subtle. One node has a different parameter, extension version, schema migration, or routing rule. Drift often hides until a failover or conflict path exercises the difference. Production readiness means setting targets for all three. What is acceptable round-trip time? What lag is a warning versus a page? How do you prove node configuration stays identical? Without those answers, the cluster may look healthy while risk accumulates. These realities also affect where you place nodes. A global mesh sounds good, but if round-trip time is high and users commonly edit the same objects from different regions, conflict probability rises. Sometimes the right design is regional write ownership with read replicas elsewhere. Architecture should follow workload shape, not a desire to make every node do everything. Technical correction for this slide: upstream lag can be inspected from the publisher view, while subscriber-side health also needs subscription statistics and relation state checks. A production monitoring story should include both sides of the replication link. Split brain is the failure mode every active design must respect. It happens when partitions cause nodes to continue accepting writes while they can no longer agree on cluster membership or ordering. The deck shows 4 defenses. Quorum means a node must have enough peer agreement before accepting certain writes. A witness can act as a tiebreaker without storing application data. Fencing prevents an isolated node from continuing to serve writes when it should step aside. Application routing keeps traffic aligned with the current ownership and health model. These defenses work best together. If a network partition happens, you want the system to degrade in a controlled way, not create too confident versions of reality. The goal is not just uptime, the goal is safe uptime. Split brain prevention is about deciding who is allowed to write when the cluster cannot fully communicate. Quorum gives nodes a rule: Continue only when enough members or witnesses agree. A witness provides a tiebreaker without storing application data. Fencing cuts off the isolated side so it cannot accept writes that the rest of the cluster will later reject. Application routing reinforces the same decision at the traffic layer. The dangerous situation is not a node going down, it is two sides believing they are both authoritative. Once both sides accept independent writes during a partition, recovery becomes a business reconciliation exercise, not just a database restart. That is why fencing mechanisms must be tested. Power control, load balancer withdrawal, security group changes, or read-only demotion are only useful if they work under the conditions that caused the partition. After a partition, the hardest question is not whether services restart. It is whether the cluster can prove which writes were accepted and which node was authoritative. That proof depends on logs, fencing records, witness decisions, and application routing history. Build those breadcrumbs into the system before you need a post-incident explanation. Additional speaker note: split brain prevention is the place where architecture and operations meet. Fencing, routing, quorum, health checks, and human override rules need to work together. The goal is not simply to restore service quickly. The goal is to avoid creating two valid-looking histories that later require emergency reconciliation. Technical correction for this slide: two data nodes do not create a safe majority by themselves. A witness or quorum device acts as a tiebreaker, and fencing prevents an isolated old writer from continuing to accept traffic after the cluster has moved on. A multi-master cluster that is not observable will eventually surprise you. This monitoring slide focuses on the signals that tell you whether replication is healthy. Replication lag tells you how far subscribers are behind. Slot health tells you whether retained write-ahead log is accumulating and threatening disk capacity. Conflict frequency tells you whether the application is creating more concurrent write contention than expected. Round-trip time tells you whether the network is widening the conflict window. These are not vanity metrics. They are the operational dashboard for active-active correctness. The important habit is to alert before the user-visible symptom. If retained bytes are growing, if lag crosses thresholds, or if conflicts spike, you want the team investigating while the system is still recoverable. Monitoring should map directly to the failure modes we have discussed. Replication lag maps to stale reads and widening conflict windows. Slot health maps to write-ahead log retention and disk exhaustion risk. Conflict frequency maps to whether ownership and routing are working. Alert thresholds map to the moment when an operator must act before impact spreads. Good dashboards are not crowded, they are opinionated. Show the signal, show the threshold, show the owner, and link the runbook. Also capture trends. A single lag spike may be harmless, lag increasing every afternoon is capacity planning. A single inactive slot may be maintenance, retained bytes growing for hours is a storage incident. Observability is not just looking at the cluster. It is turning cluster behavior into timely human action. Alert quality matters. A page that says replication is broken is less useful than one that says slot retained bytes cross threshold on node B, likely because subscriber C has been inactive for 20 minutes. Good alerts point to the runbook and include the first diagnostic query. The goal is to shorten time from signal to correct action. Testing needs to happen in phases, and the slide lays them out clearly. Phase 1 is pre-deployment validation, write-ahead log level set to logical, enough replication slots and senders, commit timestamp tracking if your resolution rule requires it, replica identity configured, and clock drift verified. Phase 2 is functional testing, prove inserts, updates, deletes, schema expectations, and conflict paths behave as designed. Phase 3 is performance testing, run realistic write volume, measure end-to-end visibility across nodes, and watch CPU, I/O, and replication lag under load. Phase 4 is chaos testing, kill nodes, partition the network, exhaust disk in a controlled environment, and rehearse recovery. This is how you turn a multi-master design from a diagram into an operational system you trust. The 4 testing phases are how you earn confidence. Pre-deploy checks catch static mistakes, missing replica identity, insufficient slots, wrong write-ahead log level, unsynchronized clocks. Functional tests prove the basic flows. Insert on A appears on B, conflict is triggered intentionally, the configured rule resolves it, DDL behaves as expected. Performance tests answer whether the system holds under real write volume. You need end-to-end visibility time, apply throughput, CPU, disk I/O, and slot retention under load. Chaos tests answer whether your runbooks work when things break, kill apply workers, partition regions, fill disks, promote nodes, and verify fencing. The point is not to be dramatic. The point is to discover failure behavior in a lab before customers discover it in production. Testing should also record timings. How long did the partition detection take? How long until fencing completed? How long to catch up after reconnect? How long before dashboards turned green? Those measurements become your real recovery time and recovery point assumptions. If they differ from the architecture slide, believe the drill, not the slide. This operating model slide ties the database back to the rest of the stack. At the top, the application layer should use idempotent writes, understand ownership where possible, and avoid creating unnecessary conflicts. The write router should direct requests to the write node based on tenant, region, or ownership rules. The database layer is the active-active mesh, but it should be treated as infrastructure as code, same extensions, same parameters, same schema discipline across nodes. Observability sits alongside the whole stack because you need to see lag, slots, conflicts, and node health continuously. Finally, change management matters. Schema changes, node additions, failovers, and upgrades should be rehearsed and automated. Multi-master is not a single feature you turn on, it is an operating model that combines application behavior, database rules, and production discipline. The operating model is where architecture becomes routine. The application layer should use idempotency keys, ownership-aware writes, and retry behavior that does not create duplicate business events. The write router should encode ownership and health decisions, not just round-robin traffic. Infrastructure as code should build nodes from the same definition so parameter drift does not creep in. Monitoring and disaster recovery runbooks should sit beside the cluster, not in a separate forgotten wiki. Change management matters too. Schema changes, extension upgrades, node additions, and failover drills should have owners and review gates. A multi-master system can be reliable, but only if the people operating it treat replication as an always-on discipline. The technology gives you possibility, process turns it into uptime. The operating model should be owned by a team, not by a document. Someone must review drift reports, maintain runbooks, update dashboards after incidents, and verify that new application features respect ownership rules. Multi-master is a living system. Its reliability depends on routine care, not a one-time implementation project. Additional speaker note: the operating model is the maintenance system for correctness. Dashboards, backup validation, schema governance, conflict reviews, and drills are not paperwork. They are the controls that keep a sophisticated replication topology understandable after the initial implementation team has moved on. Schema management deserves its own slide because it is one of the easiest places to break logical replication. In core Postgres, DDL is not part of the logical replication stream. If you run an alter table on node A, node B and node C do not automatically receive the same schema change. That creates drift, and drift can break apply workers or produce subtle application failures. The slide contrasts that manual reality with automatic DDL replication in PG Edge. The value is not just convenience. It is reducing the chance that one node has a different table definition during active writes. Even with automation, the discipline remains the same: plan schema changes, apply them consistently, validate them everywhere, and treat schema as cluster-wide state rather than a local edit. Automatic DDL replication addresses a painful class of operational errors. In core logical replication, data changes flow, but DDL does not automatically follow. That means a table altered on one node may receive replicated rows on another node whose schema is still old. The apply worker then fails, or worse, the application sees inconsistent capability by region. The left side of the slide shows the drift clearly. The PG-edge path is valuable because DDL can be coordinated cluster-wide, reducing manual synchronization mistakes. But automatic does not mean careless. You still need compatibility planning, migration windows for risky changes, and rollback thinking. Additive changes are easier than destructive ones. Index builds, column defaults, and constraints all have operational cost. The goal is not just to broadcast DDL, it is to keep schema as consistent cluster state. For DDL, remember that automatic propagation still deserves review. Adding a nullable column is usually low risk. Dropping a column, changing a type, or adding a constraint can be disruptive. The safest teams classify DDL changes, test them against replicated staging clusters, and maintain backward-compatible application deployments so database and code can roll forward safely. Production qualifier for this slide: automatic DDL and near-zero data loss depend on replication lag, supported object types, change discipline, and operational guardrails. Present these as achievable operating goals under constraints, not as unconditional behavior in every topology. Adding a node is a moment where operational discipline shows up. The Zoden workflow on this slide is designed so traffic continues while the new node is introduced. First, Zoden creates the required replication slots and subscriptions while the existing nodes keep serving the application. Second, the new node takes an initial copy and then catches up by applying ongoing changes from the cluster. Third, once it reaches the current replication position, it is promoted into the active mesh and begins participating as a full peer. The same pattern helps with replacement, scale-out, and major version upgrade workflows. The key idea is controlled membership change. You do not want node addition to be a weekend maintenance ritual. You want it to be a repeatable, observable operation. Adding in node tests whether your automation is real. Manually building subscriptions and slots while traffic is live invites mistakes, wrong credentials, wrong publication, missing table, or inconsistent initial copy. Zoden automates the membership workflow. Existing nodes continue serving traffic while the new node subscribes and catches up. The initial sync brings base data across, ongoing replication closes the gap, promotion enables writes only when the node is ready. The same model is useful for replacement and upgrades because it avoids treating topology changes as rare hero work. The operational promise is zero downtime, but the engineering requirement is observability. You should be able to see catch-up position, remaining lag, slot state, and promotion readiness before allowing the new node into the active mesh. Node addition also has security and capacity implications. The new node needs credentials, network access, slot capacity, storage sizing, and monitoring enrollment before it carries traffic. Automating subscriptions is only part of the job. The node must enter the same operational envelope as the existing peers, backups, alerts, runbooks, and ownership policy. This is where the pieces come together in PG-Edge Spock. Spock is a Postgres extension for active-active logical replication. It is not a fork of Postgres, and it does not require changes to the Postgres core. In the diagram, nodes in the US, EU, and AP regions can all accept reads and writes, while Spock handles origin tracking, loop prevention, replication between peers, and the mechanics needed for convergence. The important point for architects is that Spock builds on standard Postgres concepts rather than replacing Postgres with a different database. You still need the design discipline we discussed: identity strategy, conflict rules, monitoring, schema control, and split-brain protection. Spock gives you the replication machinery. Good architecture tells that machinery what safe behavior looks like. Spock is the technology layer that packages many of these active-active mechanics for standard Postgres. The important phrase is standard Postgres. This is not a fork that asks you to abandon your ecosystem. It is an extension that adds bidirectional logical replication behavior, origin awareness, and active-active coordination on top of familiar database operations. But no extension eliminates the need for design judgment. Spock can move changes, tag origins, and support the mesh, you still decide identity strategy, conflict rules, ownership, monitoring thresholds, and split-brain policy. That separation is healthy. Database technology should provide reliable mechanisms, while architecture defines safe use. When those two line up, active-active Postgres becomes an operational pattern rather than an experiment. This is also where standard Postgres expertise remains valuable. You still inspect catalogs, reason about slots, tune workers, manage indexes, and read logs. Spock extends the replication model, but it does not make Postgres knowledge obsolete. In fact, active-active deployments reward teams that understand both the extension behavior and the underlying database mechanics. Additional speaker note, PGEdgeSpock can reduce the mechanics of active-active logical replication, but it does not remove the need for disciplined design. Clear identity strategy, tested conflict handling, controlled DDL, monitoring, and realistic recovery procedures remain the difference between a powerful architecture and an operational risk. Production qualifier for this slide, PGEdgeSpock reduces the mechanics of active-active logical replication, but it still depends on identity strategy, conflict resolution, DDL governance, monitoring, and recovery drills. The tool helps, but it does not replace design discipline. Let me close by connecting the thread across the whole deck. We began with physical replication and write-ahead log streaming, excellent for high availability, but built around one primary writer. Then we moved to logical replication, where row-level changes flow through publications, subscriptions, and slots. From there we built the multi-master model. Every node can accept writes, publish local changes, and subscribe to peers. That model creates real benefits, but it also demands real controls, identity that cannot collide, deterministic conflict handling, origin-aware loop prevention, schema discipline, monitoring, testing, and safe node operations through tools like Zoden and PGEdgeSpock. If you are evaluating active-active Postgres, the question is not just can we replicate writes. The question is can we operate the rule system around those writes? Thank you, and I am happy to take questions. For the closing, I want to leave you with a checklist you can take back to your own environment. First, identify which workloads truly need multi-writer behavior and which only need read locality or failover. Second, fix identity before you create a mesh. Third, write conflict rules in business language and then implement them consistently. Fourth, monitor lag, slots, conflicts, clocks, and routing health as first-class signals. Fifth, rehearse the failure modes, partitions, node loss, drift, and schema change. If those items are not in place, pause before calling the design production ready. Multi-master is powerful because it gives users local write availability and teams flexible topology. It is safe only when the rule system around it is explicit, automated, and practiced. Thank you, and I am happy to take questions. My final recommendation is to run a tabletop exercise after this talk. Take one table, one tenant, one conflict, one node failure, and one schema change. Ask the team what happens, who is paged, which query proves state, and what the user sees. If that conversation is crisp, your design is maturing. If it is vague, you have found the next work item.